In this lecture, I am going to present what is Kanis method, what are the sign conventions used for the moments and slope, what are the different cases to be analyzed by Kanis method, then detail theoretical approach how to analyze the member without translation of joints, then what is rotation factors, then how to find out the rotation moment, then how to find out the final moments, then the step-by-step procedures how to solve the continuous beam without translation of joints. First, coming to the introduction. For the analysis of indeterminate structures such as continuous beams and frames, already you know the classical method such as slope deflection method and moment distribution method. A combination of these two methods has been developed by Gaspar Kanis, a German engineer, in 1947 to solve the problems involving the indeterminate structures. Kanis method is an excellent extension of slope deflection method, and at the same time it carries the simplicity of moment distribution method. Like moment distribution method, Kanis method is also based on iterative technique instead of solving the simultaneous equations, as in the case of slope deflection method. Kanis method has been found to be extremely useful to solve the problems of indeterminate structures manually, and this method is very much useful for the analysis of multi-storied frames. In this method, the member and moments of a structure are expressed in terms of the fixed end moments as well as moments induced by rotation and displacements of the end of the member. Then the equilibrium equations of the joint is written. On the basis of the relative stiffness of the members, the rotation factor is calculated. Then the total of the end moments and the rotation moments of a particular joint in proportion to their rotation factor of each member meeting at the joint. This exercise is carried out for all the joints in the structure one by one till the distributed moments in successive iterations are almost the same. And this method is first explained for structures with fixed ends, then the modification done to handle simply supported and overhanging ends. Then coming to what are the sign conventions used for the moment. As you know, in the slope deflection method and moment distribution method, the clockwise end moments are taken as positive and anti-clockwise end moments are taken as negative. Then coming to what are the sign conventions used for the slope. As you know, in the slope deflection method, the clockwise rotations are positive and anti-clockwise rotations are negative. In this method also you have to use the clockwise rotation positive and anti-clockwise rotation negative. Then coming to what are the different cases to be analyzed by Kanis method. The first case, so we will discuss the members without translation of joints. Then the second case, the members with the translation of joints. Then the third case, frames without lateral translation of joints. Then the fourth case, frames with the lateral translation of joints. Here we will discuss in Kanis method the continuous beam or the frames without translation of joints and with the translation of joints. The frames with lateral translation of joints, so there is also two cases. So the first case, that is the frames in which all the columns in a story have the same height, and frames in which the height of the column in a story are different. We will discuss when the column heights are same and when the column heights are different. Also we will discuss in Kanis method when the axis of symmetry passing through the midspan of the beams and the line of symmetry passes through the columns. These cases we will discuss in the Kanis method. First, coming to members without translation of joints. So look at this figure 1a. So this is beam in a continuous structure. So this is the member AB is an intermediate member of beam or frame which has no relative displacement at the ends. That is, the ends A and B are at the same level, and the member is subjected to the transverse loading. So the figure 1b, this is the general deflected shape of the member under the loading. Let MAB and MBA be the final end moments of beam AB. Then look at the figure 1c. So this is the fixed end moments. So first assume the ends are fixed and you have to find out what is the fixed end moments as given in the figure 1c. Then look at the figure 1d. So this is the moment due to the rotation of end A. Here you have to find out, due to the rotation of end A, what is the rotation moment induced at A and at B. So the rotation moment induced at A is 2m dash AB and the rotation moment induced at B is m dash AB. Then look at the figure 1e. So this is moment due to the rotation of end B. So here the end A is fixed and the end B is simply supported, and due to the rotation theta B, what is the rotation moments induced at the end of the member A and at the end of the member B. So at the end of the member A is m dash BA and at the end of the member B is 2m dash BA. The actual end moments in a member AB may be calculated due to the following cases. First, you have to assume the member AB as a restraint or completely fixed, and you have to find out what is the fixed end moments, that is MFAB and MFBA at the end of the member. So here you have to take theta A is equal to theta B is equal to 0. Figure 1c. So here you have to assume the ends are fixed or fully restrained, and you have to find out what is the fixed end moment MFAB and MFBA. Then in second case, only the end A is rotated through an angle theta A, including a moment 2 m dash AB at end A and m dash AB at the further end B. Then moment m dash AB is called the rotational moment at end A. So here you have to allow, so here you have to take B as a fixed end and A is a simply supported end. Allow for the rotation, and due to this rotation theta A, so what is the rotational moment induced at the end of the member A, and what is the rotational moment induced at the end of the member B, that you have to find out. Rotational moment induced at the end of the member A, that is 2 m dash AB, and the rotational moment induced at the end of the member B, that is m dash AB. Then the third case, that is the find A is fixed only and B is rotated through an angle theta B, which includes a moment 2 m dash BA at B and moment m dash BA at end A. The moment m dash BA is called the rotation moment at end B. Then in next case, so you have to take A as a fixed end and B as a simply supported end, and you have to take the rotation theta B at the end B. And due to this rotation, due to this theta B, what is the rotation moment induced at the end A and at the end B, that you have to find out. So the rotation moment induced at the end A, that is m dash BA, and the rotation moment induced at the end B, that is 2 m dash BA. So the final moment that you can find out, that is MAB is equal to MFAB plus 2 m dash AB plus m dash BA. Similarly, at the end B, the final moment MBA is equal to MFBA plus 2 M dash BA plus M dash AB. So M dash AB and M dash BA are called the rotation contribution. The moments M dash AB and M dash BA are called rotation contribution. This is called the rotation moment. So the final moment can be calculated by taking the fixed end moments plus twice into rotation contribution of near end plus once into the rotation contribution of the far end. So here you have to find out the final moment MAB. This is the fixed end moment and this is the twice into the rotation contribution of the near end moment, and this is the 1 into the rotation contribution of the far end moment. Similarly, MBA is equal to the fixed end moment MFBA plus twice into the rotation contribution of the near end plus 1 into the rotation contribution of the far end. This is the expression. So by using this expression you can find out the final moment. Then look at this figure. This is the building frame. If no translation of joints occurs, equation 1 is applicable to all the members. So this is the equation 1. So this equation is applicable to all the members. Let us take the joint A, and this is the member AB, this is the member AC, this is the member AD, and this is the member AE. All the members, the AB, AC, AD and AE are meeting at the joint A. Then due to the no translation of joints, the equation is applicable to all the members. This is the equation 1 and this equation is applicable to all the members. So you can find out what is the moment MAB, MBA, MAC, MCA, MAD, MDA and MAE, MEA. So consider the member meeting at joint A in the frame as shown in figure 2. So this is figure 2. Now the end moments at joint A according to equation 1. So MAB is equal to MFAB plus twice into M dash AB plus M dash BA. Similarly, MAC is equal to MFAC plus twice into M dash AC plus M dash CA. Then MAD is equal to MFAD plus twice into M dash AD plus M dash DA. Similarly, MAE is equal to MFAE plus twice into M dash AE plus M dash EA. So this is equation 2. So you can find out easily what is the moment MAB, MAC, MAD, MAE by using this expression. As you know, for the equilibrium of joint A, the sum of end moments at end A must be 0. The summation of MAB is equal to 0. Here there are 4 members meeting at joint A. So the sum of the moment, so that is the summation of MAB, that is equal to 0. MAB plus MAC plus MAD plus MAE are equal to 0. Summation of moment MAB is equal to 0. So you know MAB is equal to MFAB plus 2 M dash AB plus M dash BA. So here you have to take the summation of this moment and summation of this moment and summation of this moment. So summation of this moment, that is summation of MFAB plus twice into summation of M dash AB plus summation of M dash BA, 0. Summation of MFAB plus twice summation of M dash AB plus summation of M dash BA is equal to 0. So this is expression 4. The summation of MAB, this is the sum of near end moments in the member meeting at joint A. Summation of MFAB is equal to sum of fixed end moments of all the members meeting at joint A. Summation of M dash AB is equal to sum of near end rotation moments of all the members meeting at joint A. And summation of M dash BA is equal to sum of far end rotation moments of all the members meeting at joint A. Then from the equation 4, we have summation of M dash AB is equal to minus half into summation of MFAB plus summation of m dash BA. Then after simplification, summation of m dash AB is equal to, so minus of into MFA plus summation of m dash BA. So summation of MFAB is equal to the MFA. At joint A, there are 4 members meeting. So you have to take the fixed end moment of all the members which are meeting at the joint A. So that is the summation of MFAB, that is equal to MFA. Sum of fixed end moments at joint A, MFA is equal to summation of MFAB is equal to sum of fixed end moments at joint A. And from the moment rotation relationship, you know 2m dash AB is equal to 4EIAB theta A by LAB. But you know IAB divided by LAB, that is equal to KB, the relative stiffness of the member. So here you have to put, instead of IAB by LAB, so put KB. So 2m dash AB is equal to 4E KB into theta A. Similarly, you can find out m dash AB is equal to 2E KB theta A. At joint A, all members undergo the same rotation theta A. So assuming E is same for all the members, then take the summation of m dash AB is equal to 2E theta A, summation of K into AB. The sum of the relative stiffness of the members which are meeting at the joint A. So this is equation 9 and this is equation 8. So divide equation 8 by equation 9, that is equation 8 m dash AB is equal to 2E KB theta A, and from equation 9 summation of m dash AB is equal to 2E theta A summation of KB. So divide this equation 8 and equation 9. So here you can find out MAB divided by summation of m dash AB is equal to KB by summation of KB. So here 2E theta A cancel. After cancelling 2E theta A, then you have m dash AB divided by summation of m dash AB is equal to KB by summation of KB. Then from this relation, m dash AB is equal to KB divided by summation of KB into summation of m dash AB. So this is expression 11. Then substituting equation 6 in the equation 11. As you know, in the expression 6, summation of m dash AB is equal to minus of into MFA plus summation of m dash BA. So put the summation of m dash AB value in the expression 11. After substituting the equation 6 in equation 11, then m dash AB is equal to KB divided by summation of KB into minus half into MFA plus summation of m dash BA. Then m dash AB is equal to minus half into KB by summation of KB into MFA plus summation of m dash BA. This is expression 12. In this expression, so minus half KB by summation of KB, so this is called the rotation factor. The expression minus half KB by summation of KB is known as the rotation factor for the member AB at joint A. Denote the rotation factor as UAB. So UAB is equal to minus half into KB divided by summation of KB. So this is expression 13. Equation 12 can be written as, so you know in equation 12 m dash AB is equal to minus half KB by summation of KB into MFA plus summation of m dash BA. As you know, minus half into KB by summation of KB is the rotation factor. So that you can denote by UAB. You can write m dash AB is equal to UAB into MFA plus summation of m dash BA. So here you can write m dash AB is equal to UAB into MFA plus summation of m dash BA. So in this equation, the summation of fixed end moments MFA is a known quantity. To start with, the far end rotation moments m dash BA are not known, and hence they may be taken as 0. By a similar approximation, the rotation moments at other joints are also determined. So this is the expression. So by using this expression, you can find out what is the near end rotation moment. You know what is the fixed end moment of the joint A, and you don't know what is the rotation moment of the far end. So the rotation moment of the far end in first cycle you have to assume as 0, and you have to find out what is the rotation moment of the near end M dash AB. Similarly, the rotation moment at other joints are also determined. Then coming to what are the important points, the sum of rotation factor at joint is equal to minus half. So always you have to check the sum of rotation factor at joint should be minus half. Then if an end of a member is fixed, the rotation at that end being 0 and rotation moment is also 0. You have to take, if an end of a member is fixed, the rotation at that end is 0 and the rotation moment is also 0. Then if an end of a member is hinged, it is convenient to consider it as fixed and take the relative stiffness as 3/4 I by L. And for all other members, you can find out the relative stiffness by taking I by L. Then coming to what are the step-by-step procedures to solve the continuous beam or frame without translation of joints. So these are the steps. The first step to determine the fixed end moments. The first step you have to assume the ends are fixed and you have to determine the fixed end moments. Then in second step you have to find out the relative stiffness of the members. Then you have to find out the relative stiffness of the joints. Then you have to find out the rotation factors. Then determine the rotation moments by iterative process. Then determine the final moments. So these are the steps you have to remember when you have to solve the indeterminate structures by Kanis method. Now all are clear. What is Kanis method? Then how to analyze the indeterminate structures, that is members or frames without translation of joints.